So hello all, thanks again for joining us. My name is Robert Benkove. I'm one of the automation specialists for Turtle & Hughes. Joining us again today, we have Casey Klawicki, our co-host, message chat monitor, and Turtle & Hughes automation specialist. Being that our guest presenters today are Pete and Rick from the Fluke Corporation, the subject matter is on measurement tools for troubleshooting issues related to variable frequency drives. So with that, we also have with us today Turtle & Hughes drives and motion specialist, Lorenzo Paganotti. Thanks all for joining us today. Rick, please introduce yourself and take control of the meeting.
Thank you, Robert. Pete, while I'm trying to figure out how to share my screen, you want to go ahead and introduce yourself?
Absolutely, Rick. Hey, everybody. Thanks for joining us today. My name is Pete Stormer. I am the New York Area Territory Sales Manager for Fluke Instruments. So I am the person that would work with your local Turtle APR to help you get the tools you need to solve the problems you're facing in your facility, whether it's a production line issue, electromechanical, or other facilities type of issues. And if you have other counterparts in your organization that would be also beneficial for us to speak to and meet with to help solve any issues, please reach out to your Turtle & Hughes local contacts, and we can be in there to bring some demo, show you how we can help you solve problems. Because that's really what we look for. We look for ways to get to the root cause of an issue, and we want to help solve a problem, not just fix the glitch, as they say. So, Rick, you pretty close there yet?
I'm good to go. Am I sharing the screen?
You are indeed.
Yep, you're good to go.
Yeah, and I'm Rick Kleino. I'm the or one of the sales application managers. You probably already figured out I'm down in North Carolina. Or somewhere in the South. I'm going to talk as fast as I can because I know this is you're a group I'm not used to speaking to. Y'all talk too fast for me. I'll do the best I can. Talk about measurements primarily because we're the Fluke guys. Measurement tools. Choosing the right tool for measurements on VFDs. And Lorenzo, we have not met, but I know you're the drive specialist. I'm not a drive expert by any means. I'm going to be talking about drives a lot. So if I say something wrong and you want to correct me, you just jump in. Just don't embarrass me in front of everyone, but don't let me mislead your customers.
I promise I won't, Rick.
Okay. Something that I'm going to use this expression when we talk about drives. We'll talk about power quality a little. We'll talk about nonlinear loads. Drive is a great example of a nonlinear load. When you're talking nonlinear loads, power quality and that type measurement is always a part of it. This is outline. I don't know that we'll get all the way down to number 4, but we'll start off and talk just a bit about safety standards for low voltage test equipment. Low voltage being less than 1,000 volts. When you're talking about drives, you're probably talking about 3-phase power systems, and safety's an important consideration. The tools you're using to make these measurements. Then we're talking about measurements on the line side or the input side of the drive, down over here on the left, versus on the output side of the drive. The drive presents some challenges from the measurement standpoint, and I'll show you some pretty high-end equipment, actually, PowerLoggers, scope meters, but I really want to emphasize the importance of having the right tool when we're just talking about the everyday things, voltmeters, clamp meters, and some of the specifications that are important. And it differs on the input and the output side of the drive. And then as much as we can, we'll talk about measurements on the drive train. These are mechanical thermal measurements. But first, safety. Now, I'm going to assume everybody knows what NFPA is. Everyone knows the term arc flash. What you might not know is that NFPA classifies your voltage measuring equipment as part of your PPE. So if you look at the gentleman over here holding the scope meter, his glasses, his gloves, and his meter are all part of his personal protective gear. Generally, the first job of a piece of test equipment where you're measuring voltage is to protect the user. NFPA 70E doesn't say a whole lot, not a lot of detail about your test instruments. They point you to another safety standard. which all comes from the IEC 61010 and international standard. I'm guessing that those of you who are meter users probably know the term Cat 3. The category rating system comes from this IEC 61010. There are three categories. They discontinued the first one here. But I would just generally recommend, if you're working around drives, or really in three-phase power distribution systems, there's both the category, Cat 3 refers to distribution wiring versus just receptacle loads, right? But there's also a voltage rating. So if it just says Cat 3, it doesn't mean anything. It's got to be Cat 3 600, Cat 3 1000, etc. And we recommend the Cat 3 1000 volt rating, especially when you're working around drives, because you can get transients or reflections out of the drive that can be fairly high voltage. And the safety, which in my mind, cameras are turned off, you can't tell I'm gray-headed and old. But to me, this is kind of a new standard. If you look at the bottom, it was implemented in the 90s to provide protection or better protection against voltage transients, which is one of the major components of this new standard. But it's, a Cat 3 1000 volt meter, it just has a much more robust front end as far as protecting itself and therefore the user from voltage spikes. But if you're not sure about the safety rating on your meter, it should be marked right by the terminal inputs where the voltage leads go. So Cat 3 1000 volts is what we'd like to see. Most of ours with that rating are also Cat 4 600. That's dual rated. Category 4, for the most part, is the utility side of a rate meter. But a special note, because we're going to be talking about oscilloscopes, if you look at the guy holding the scope probe here on the right, that's the signal input, and the alligator clip here, the little black lead is the reference. It takes 2 leads to measure voltage. You have to be careful. Anytime you got an instrument with multiple input channels and you're making power measurements, you need to understand common inputs, isolation from earth ground. If you look back at the inputs to the scope here, this is a 4-channel scope. Typically on scopes, if I'm connected to channel A, like this is, there are 2 conductors here, the reference and the signal input. Typically on scopes, these reference inputs are all tied in common. So if I make a phase-to-phase voltage measurement here, and that little black clip is on phase B, that means that the black clip for these other 3 are on phase B too. Also, if you've got a benchtop scope with metal BNC connectors, these things are connected to earth ground on the plug of the scope. So making power measurements with scopes, you need to be sure you got the right isolation between channels. You can let the smoke out of the scope very quickly, trying to make phase-to-phase voltage measurements. So that's my safety talk. I was take a lot of time here talking about power quality. I watched one of the tech talks. It was one from June or July. Some Rockwell folks were presenting this iSense and some of their power quality tools. I was really impressed. They and the Fluke tools would, in a sense, augment something like iSense, but they're very different in the application. The Fluke power quality loggers are meant to be carried around the plant. You hook them up maybe for a month, maybe just for a few hours, but it's for troubleshooting more at the point of contact. They don't go in your switch gear. Not compatible with the iGrid software or any of that, but I was impressed. But when you're talking about variable frequency drives, they get blamed for a lot of power quality issues. It's very common for Pete and I. One of our customers at an industrial site has just had a new line put in. The systems house that installed it, if it has problems, may say, well, you got power quality. You got power issues. Maybe it's harmonics. We don't know, but our system's perfect. It's your problem. So you call the power company, they come out and they say, oh, no, our power is perfect. It's no problem. So now for Pete, now that represents an opportunity to sell a power analyzer. But often VFDs are involved, drives are tripping, or PLCs, relays are tripping. And we know something mysterious is going on, but we don't know what. So the PowerLoggers, I'll show you, that's, again, a fairly high-end tool. But really, I want you not to miss these specifications down here, and I'll illustrate this, are important for just meter users. Fluke customers are meter users. The higher end stuff, scope meters, PowerLoggers, things they pick up when there's a problem generally. So we'll talk a little about true RMS versus average responding meters. Crest factor is a spec on your meter you might not have thought about before. It's really important when you're measuring amperage into on the input side of a VFD. And then the bandwidth on the meter you're making a measurement with is important if you're on the output side of the drive. In fact, your success getting a voltage reading that matches what the VFD is showing you is going to be dependent on the bandwidth in the meter. And nobody thinks about bandwidth when they're talking about meters. You think about bandwidth on scopes, right? So here, don't be put off by this. Everything in blue in this diagram is the drive. To the left is the input or the line side of the drive. So this is voltage coming in. On the green stuff here on the right, this is where the motor is. We're converting the electrical energy coming in to mechanical energy to do work, driving pumps or whatever, move things around. But the drive has three main sections in it. And I'm thinking that most of you have heard this. You might not have looked at this detail. But step one, voltage coming into the drive of this rectifier circuit here, just a bank of typically, just diodes. You're going to convert AC to DC voltage for the DC bus. You've heard the term the DC bus, basically big capacitors, right? Then from the DC bus, this section with all the transistors in it, the IGBTs, is going to take DC and create an AC signal, an output that's kind of specialized called pulse width modulated voltage, which is what the motor sees as the PWM output. So really, in the examples I'll show you, the little drive I have three-phase motors, but I have a single-phase drive. It really doesn't matter that I have a single-phase drive or a three-phase drive and single-phase motors, because everything on the front end goes to DC, and it's a responsibility of the inverter to create the output for the motor. So, the DC bus, I guess, in theory, could be batteries or solar panels or something. It's the inverter here that's going to create that output signal. So before we start talking details about making measurements, let's say, what should we expect to see, right? On the line side, the input to the drive here, where the big number 1 is, this is just power coming in. This is power in your plant. This is three-phase voltage, probably in the neighborhood of 480 volts. The exact level may not be that important, 460, 480, 485. Balance is important. That is, the measurement between each phase should be the same. But there's another important little detail here, and that is called the peak voltage on the voltage coming in. The peak voltage you can calculate for a sine wave, and these are sine waves. We'll talk about harmonics in a bit. If I tell you something is a sine wave, I'm telling you its shape is like this, and it has no harmonic distortion if it's a perfect sine wave. But for a sine wave, you can calculate the peak voltage. It's related to the RMS voltage by the square root of 2. So if I have a 480 volt network coming into the drive, the peak voltage is around 679. The peak is important here because this becomes the level or close to the level of the DC bus. If I look at the second measurement area here, the DC bus, if I look at it on scope, DC levels aren't real interesting. They're just a flat line, but this should be roughly the peak voltage coming in. That is, that capacitor bank here. What the rectifier circuit does is charge this up to the level of the DC bus. That capacitor bank will droop over time. That voltage will drop. When it does, that rectifier on the front end will operate again and charge the voltage level back up. So you want to maintain as much as possible this constant DC level. But if you look at it, and you can see here, there's a little bit of wiggle in it. That's called ripple. And that's a ripple, that's a little AC riding on the DC bus. So here's two measurements that we can make. And this one, the ripple, will tell you a lot about the health of the front end of the drive. And I can't say much of that because we get over my pay grade pretty quickly. We talk about drives. But then the output, this to me is the really interesting part. This is the pulse width modulation. This is the voltage coming out of the drive. It looks like red smudges on the scope here, but each one of these smudges is really a string of pulses. So that's a string of pulses that are positive, a string of pulses that are negative, and then back to positive. If I zoom in on this with my scope, what I'll see are just the individual pulses. Now, because the pulses come from the DC bus, the height of each pulse should be the level of the DC bus, which is pretty close to the peak of that AC sine wave coming in. So there's some kind of reference points when you start making measurements with a fancy tool like a scope or the PowerLogger that you can look for here. But again, and I want to begin with making a few measurements on the input side of a drive. I want you not to miss the importance of just the everyday tools, voltmeters, clamp meters, and having the right specs to get the right numbers here. But if I ask you then on the input side of the drive, on the line side, what are you going to measure and what kind of tools do you use? Well, I think the obvious answer is going to be volts, amps, and hertz for sure, especially if the only thing you have is a voltmeter and a clamp meter. And when you measure volts, you should know about what that is, the neighborhood of 480 or 230, you know, depending on how the motor's set up, I guess. But voltage levels are important, but also on a three-phase system, the balance is important. That is, each phase should be about the same, right? If we look at amps, not sure what amps is, that's dependent on the load, you know, that can vary. But voltage you have a pretty good handle on, and the frequency coming in on the line side, it should be 60 hertz, right? And you can do all that with a voltmeter. Now, if you suspect power quality issues, dips and swells, things that can cause the drive to trip on an over voltage fault, transients or harmonic distortion, then you need some more sophisticated tools. Same would be true to just look at energy or power factor. What I have here is just a short video. This is a setup that I have, and it's beside me now. I've got another camera. I'll try to give you a live look at this, but too many things can go wrong when you've got a lot of equipment like this. So I just recorded a piece of it. You see, this is a PowerFlex drive sitting in an old demo kit. And over here, there's a little bitty motor. There's three-phase motor sitting here. There's the PowerFlex drive. I've got two different Fluke clamp meters. What I want to do is compare the measurements. What I'm interested really in is amps here. Now, when the video starts, I will have already made the two voltage measurements. So I'll have to disconnect, make the amp measurements. Let me run the video and then we'll talk about it.
Now we're going to make a switch and measure amps with both instruments. These little line splitters are where I'll make the measurement. Let me pull the test leads out of both of them. I'll go ahead and set them both up to read AC amps. And both meters have a hold button on the side, so I can clamp on to the line splitter and push the hold button and then just set it back on the display to read the voltage. Here's my Fluke 334 and the Fluke 376 FC. The beeping's coming from the 376. It beeps when it's in the hold mode. I think you can see both readings now, readings off both instruments. The 334 has 5.5 amps. And the 376 FC has 10.0 amps. So if you compare results, it looks like when we're measuring voltage, these things agree pretty closely, within half a volt. But when we measure amps, there's a large discrepancy, 10 amps versus 5.5 amps.
Now's the time I wish I could, we could just chat for a minute. Let me ask a question and you could stick something in the chat window if you want to volunteer a response. But if you look at this, the discrepancy here, 5.5 versus 10, that's almost 50% error, depending on how you calculate it. You might calculate it to be 100% error. So, you know, are you surprised to see two Fluke meters, and I use Fluke intentionally here, that are reading that much differently? So that's a yes or no question. The other is, what's going on? I can tell you that both meters are doing exactly what they're supposed to do. You notice when they measure the voltage, they pretty much agree. It's here on the amp readings where they disagree. You know, do you think that the problem is one of them's better at measuring volts but not too good at amps, or you know, what would you guess there? I don't know. I can't see the chat window, so I don't know if anyone offered an explanation. But here we go. I've highlighted, kind of summarized what happened here. I'm on the line side of the drive. And this is a single phase drive, even though it's a three-phase motor, which is really inconsequential. Big difference in the amp readings. I have another instrument hooked up. I could show it to you, but I'm not sure about the time, so I'm not. This is a display off of it. It's a little power quality analyzer. And you see the waveform on the top is the voltage, a nice clean sine wave. The waveform on the bottom here is the amperage. Yeah. The difference is the harmonic distortion in the voltage versus the amperage. There's no harmonic distortion in the voltage to speak of. If I compare the specs on the two meters, the one on the top, the 334, is not a true RMS meter. The 376 is a true RMS meter. If your meter's not true RMS, you have no harmonic distortion, you're fine when you're measuring. Now this applies to AC, right? But if you have harmonic distortion, which means you do not have a perfect sine wave and you don't have a true RMS meter, your readings aren't going to be right. And they can be way off, as you see. This is kind of a worst case example. I'm looking at amperage into a single phase rectifying circuit. If you looked at the amps going into the computer you're using now or the monitor, you probably see the same thing. Where the flat lines are, there's 0 amp draw. Right at the peak of the sine wave, you get a little, pulse of current into that rectifier circuit, and then it goes flat again. Then you get another little pulse of current. What's happening is the rectifier on the front end of the drive, or in this case, well, the rectifier is keeping the DC bus level up, charging the DC bus. When the voltage on the DC bus drops, you have to pull a little current off the power supply to jack that voltage level back up. And you can see this in the ripple that's sitting on the DC bus. Also, this you can see where these pulses are occurring. Another spec here, I don't have it written down. You see in red, it has, you must have a true RMS meter to measure amps going into VFD. Another spec, I mentioned it earlier, is the crest factor. We recommend a crest factor of at least 3 if you're working around drives or anywhere there's a nonlinear current like this. So office buildings, all your PLCs, your HMIs, all that stuff that runs off single phase voltage, probably, you know, if they have a computer in them, the harmonics and the amps is going to look like this. So the crest factor spec is something that it's an indication of how the meter is going to handle harmonic content. Now this, just for completion, if you look, this is a picture of voltage on top in red, current on bottom in blue. This is the voltage and current into a 3-phase drive. So you see I've got 395 volts phase to phase, 25 amps. And on a 3-phase drive, that rectifier is going to turn on 2 times every cycle. So you get 2 pulses. The harmonic distortion here is much lower, actually, than on the single phase system. I've called this total harmonic distortion, or THD. If you look at the images on the right, this is the classic way to display harmonics. If I look at the sine wave, that's the picture on the top, the voltage here. On the sine wave, there's no harmonics. There's on the bar graph, there's just 1 bar. It's at 60 hertz, or the fundamental frequency. These harmonic numbers, you have to multiply them by 60 to know what the frequency is. This is just looks like a pretty clean sine wave because I only see the 1 bar. Maybe there's a little bit here at the 5th harmonic. But if you look at this number, the upper right-hand corner of the screen, that's total harmonic distortion. THD is kind of a summary. It's actually, I think you add the square root of the sum of the squares of all the bars to get the THD, something like that. You look below, this is harmonic content in the amps. THD is 88.9. You'd like to see something below 5 in the voltage. It's just kind of a reference. On the amperage, it can be really high. It's not necessarily hurting anything. It's the way the world works right now. Harmonic distortion in the amps is generally not a problem unless the voltage supply here can't deal with the harmonics and the current, can't supply current at the harmonic frequencies, and it impacts the harmonic content of the voltage. So too much harmonics in the current can cause harmonic distortion in the voltage. In that case, you got a problem. Here's an example. If you look at the image here on the right, it shows voltage and current on the same screen. This is current into a single phase rectifier. And actually, this is 4 or 5 of the VFD demo kits. Pete, I don't know if you have one of the big black boxes with a 1/4 horsepower motor and a drive in it, but we had about, I don't know, maybe 5 of these things together. We've just gotten them. They were all plugged in on 1 extension cord. So every drive is drawing current here at the peak of the sine wave, negative and positive, to try to maintain the level of the DC bus. And if you look at the sine wave for the voltage, you see it's no longer purely sinusoidal. It's flat topping here. That level should be up, you know, quite a bit higher. The drives were running fine, didn't hurt anything, but remember, it's this peak voltage that generates the DC bus. So you can have what looks like and measures like with a regular meter, pretty good voltage. But if you don't have enough on the peak here to run the DC bus or the computer at whatever voltage level it needs, then you've got trouble. Well, just a little note. Now, Fluke has, I think there's 17 different model numbers of power quality analyzers. Two main applications for these guys. One is just a load study or an energy audit. You know, I want to know what it costs to run a machine or just what my load is. These things they'll all monitor for a long time, and any of the power loggers can do this, or any of the ones we have. I imagine anybody's can. It's when you start troubleshooting the second application, power quality problems. The ability to capture events is kind of the key word, event here. Faults like dips, swells, transients is what separates those 17 loggers from one another. Here's a pretty typical example of a voltage dip. You look at the right. The logger had been running probably not long. I think I did this on a demo board. But while we were logging volts, amps, hertz, power factor, all that stuff, the voltage dropped. And if you look at the event report here, the event table, we had a dip and it lasted, that's 108 milliseconds, 0.108 seconds. You know, a dip is an event where your voltage drops a certain percentage, typically a 10% window for nominal voltage. And the duration is something longer than 8 milliseconds, half a cycle of a 60 hertz waveform. So we had 108 millisecond dip. If you look at the RMS voltage, what you'd read on a meter, you see we call that the RMS profile. But if you see it on an oscilloscope, this is what we would call a snapshot of the waveform. So you see where the voltage just disappeared and came back. And depending on the logger, you may or may not have these things at the bottom, you know, this kind of detail. Maybe it's just the digital readout. Speed determines the cost of a logger. There are a lot of little details there. I want to show you now. This what you're getting now really is a word from our sponsor. Pete can give you more details on this, but the clamp meter I used in the little video was a 376. This one's new. It's a 378, and FC means Fluke Connect, so it can log readings into memory. You can connect it to a smartphone and pull the readings out or get the display remotely. But I want to show you a couple of things about this. Well, first is field sense. It's kind of the big deal that we're advertising. If you look at this display, you see there's only one test lead coming out, and it's grounded. So what we're doing here is making a non-contact voltage measurement. Through the jaws of the clamp, we're measuring both amperage, standard clamp meter, but also voltage. So you see 13 amps and 234 volts. This to me is a safety feature in that I don't have to put a test lead on a hot conductor up here, which is nice. But also, and just for the context here, we have something called power quality indicators. So you see PQ for amps, PQ for volts. The last one here is power factor. It doesn't really measure and display the total harmonic distortion, but it gives you an indicator if the THD reaches certain thresholds, both for voltage and for current. So I think that's kind of unique. Pete can give you details on that. And I'm sure you can buy them at Turtle and Hughes. Now, this is another word from our sponsor, but this kind of introduces the next section of what we want to do here. This MDA 550, MDA's motor drive analyzer. Okay. Well, there it is spelled out here. And it is, in fact, a scope meter. We sell a lot of different scope meters. The MDA 550 is a 4-channel, 500 megahertz scope meter, but it has one extra button on it. It has firmware in it to help you make measurements on VFDs. Our customers tend to be meter users, not scope users. And if you're going to troubleshoot, you look to the right, you see that PWM signal coming out of out of the drive. If you're going to troubleshoot the ripple on the DC bus or reflections, if you really want to get a handle on what's happening on the output side of a drive, you have to have a scope. Scope has to have the right safety rating, and be able to handle complex waveforms. So hence this little firmware package to help you figure out how to make the measurements. And if you look, it'll give you a menu with options, what you want to measure. When you choose something, it'll give you a little wiring diagram of just where to put the probes. It has a help screen built into it. I don't think they call it help. I think they call it just information, but this will tell you about the measurement that you've chosen. And then there's some other little help, little aids. One, the scope will set itself up for the measurement and give you a display like this. You don't have to fiddle with trigger levels. It's all done automatically. And if you want to, in this example, I want to zoom in on the PWM signal and see individual pulses. Now, if you're a scope jockey and you use a scope, you know that's easily done with the time-based button. But here, for those who aren't scope jockeys, we put a zoom key. Everybody understands zoom, so I just push the zoom button. There's several places where the menu system just helps you look at the waveforms and focus on your measurements and not worry about how to push buttons on the scope. Another little comment here, if a Rockwell service guy comes into your plant, he may well have a Fluke scope meter, but his interest is different than most of our end user customers who have these things. Yeah, you can troubleshoot the VFD itself, but generally what our customers are looking for are just what is the drive doing in its environment. Is there something happening on the front end that might upset the drive, or is the drive putting harmonics out? And that's kind of a tricky, I probably shouldn't have said that. But you can look at things like harmonic distortion on the front end of the drive. On the back end of the drive, do you have reflections that can damage the insulation of the cabling going out to the motor, or cause the motor to fail because you're damaging the insulation? You can have mechanical problems, thing called fluting in bearings, which drives get blamed for a lot, but not always the cause. But for our customers, I think this is more about just looking at the electrical input, the output, and understanding the environment that drives in. Is it hurting something else? Not so much troubleshooting the drive. Well, I think I jumped over something. Let me go back to the PowerLoggers. Power quality analyzers, just the PowerLoggers in general, we do not recommend using these on the output side of a VFD. Okay, there's kind of one exception to that, but generally the PowerLoggers, they understand a three-phase or single-phase or split-phase power network. You hook them up and say, I've got a three-phase delta or a three-phase Y. They understand that. They'll show you where to connect all your probes. If you take something, even the MDA still, it's hooking up's a challenge, and you can't get all the voltages and currents at the same time with a 4-channel instrument. So generally, we don't recommend the scope meters to troubleshoot, say, a power issue in the power network. And the PowerLoggers, we don't recommend for the output side of the drive because they're really set up, their measurement technique, which is governed by international standards, for a 60 hertz fundamental frequency, or in Europe, you can have a 50 hertz fundamental frequency. Or on ship, maybe 400 hertz fundamental frequency. But the output of a VFD, the V in VFD is variable frequency. So that's why you can't use the PowerLoggers on the output. But here's my motor drive MDA 550. I'll just show you what the menus look like here. If I want to make a measurement on the input side of the drive, tell it I want to measure volts and amps, phase to phase. Gives me the wiring diagram, and here is the voltage and current into a three-phase drive. You saw that. It does have the harmonic measurement for the line side of the drive. And again, this is something you can do with any scope meter. They have a fast Fourier transform. They can do the arithmetic to give you the frequency domain graph that is the harmonic screen here. But on a regular scope meter, it doesn't give you harmonic numbers and nice clean bins. It would look more like a spectrum analyzer. But this also calculates the THD for volts and amps. Unbalance is critical measurement on the line side of the drive. So this shows me all three waveforms, and where my cursor is, it's calculated the unbalance. Generally, these readings at the top can be recorded over time too. So I think I've got an unbalance problem, but it only happens when a machine next door turns on. I can record for days, the volts, amps, the unbalance, these readings at the top. So moving from drive input measurements to the DC bus, and I'll just show you an example here. We picked DC bus out of the MDA menu. Want to look first at the DC level, so that's here. And I can choose the AC ripple on the bus. The AC ripple is just blowing up that little bit of wiggle that you see in the DC level. And if you're a scope user, you can do that. You can AC or DC couple the measurement input on a scope typically. If I take the DC out and I'm AC coupled, I'm only looking at the AC waveform here. So now I can blow it up. That's a signal that you see I'm at 1 volt per division on the scale here for the ripple. But this guy is should be close to 700 volts, right? Well, 596 volts. That's why you can't see a 1 volt ripple sitting here. You have to be able to separate the two. And with the firmware loaded in the MDA, that's easily done. Now, if you know what you're doing, you can look at this. This is a 6-pulse drive. You can count 6 pulses, 1, 2, 3, 4, 5, 6, and then it starts all over again. I don't know enough about it to tell you, but those diodes on the front end, that rectifier circuit, if one's not firing right or it's missing, you can use this to troubleshoot that. But most of our customers really aren't even going to look at the DC bus. They're worried about the input side and the output side. Now I'm looking at 1044 on my clock, and I know we wrap it up by 11, a little sooner if we can. But I want to take time to show you on the output side of the drive. To me, this is more interesting. So I'm going to try to make a live measurement here and show you that with another camera. But if I ask you again, what are you going to measure? What kind of tools do you need? Volts, amps, hertz comes up. Unbalance is important for volts and amps. But reflections is something that we didn't have on the input side of the drive. Harmonics, power measurements, the things that a power logger can do easily, you can't put it on the output side of a drive. I don't think it much reason to measure harmonics on the output anyway, because it's there. If you want to know the power, how much energy this thing using, make the measurements on the line side of the drive. But I'm going to hook up, you see the lower right-hand side of the screen here. Let's see if I can turn my other camera on. There we go. So what you're looking at now is a little camera that's behind me. You see there's my drive. I'm going to start it. It's not too noisy. I've run the carrier frequency up on my drive to about 8 kilohertz, so they're not as noisy. Normally the carrier is around 4 kilohertz. But you see a little bitty motor. I don't know if you can tell that thing's turning or not. And here to the right, let me swing the camera around, is a scope meter, which is measuring, and there's my measurement connections here. This little box is my scope probe. And then back in the far side of the picture is a terminator. That's kind of an integral part of my setup here. I'll tell you why in a minute. And again, that's something Lorenzo can address better than me. But what I want to do is just show you first what PWM looks like. Okay? So I can control the speed of the drive, by turning this little knob, which is the speed of the motor. To me, it's a wonderful invention that you can turn a little knob and change the rotational speed of a motor. When I was young, you couldn't do that. It took gears and belts and, But I'll show you, we'll watch how the waveform changes on the scope as I change the speed of the motor. If you look at this, I call this the envelope, the red smudges. Now the pulses are buried in there, but imagine a sine wave just kind of drawn here. That's what the motor's responding to. The motor doesn't have the bandwidth, or the motor cannot respond to the pulses. So it follows the envelope here, and I'm just going to slow the speed down. You'll see voltage and hertz at the top changing. That waveform stretches out, right? I've got the frequency so low now that the scope meter doesn't know what to make of this. It doesn't know how to calculate readings. It sees a string of positive pulses, then they go negative, and then a string of positive pulses. It can't calculate, this. There's not repetitive cycles there on the screen, so it's not real sure what to do. But what I'm going to do now is just zoom in here by controlling the scope. Just punch the time base. If you're a scope guy, this is easily done. And there's pulses. That's where the magic is on the drive. The height of each pulse should be the level of the DC bus, right? Or it is the level of the DC bus. The spacing between pulses doesn't change. That is determined by the carrier frequency. Now, what I'm going to do is speed the motor back up, and you'll see the pulses change. The pulses get a little wider, they don't get any taller, and the spacing between the pulses doesn't change. It's the width of each pulse. So it's pulse width modulation. And if you look at, let me go back to showing the full envelope. If you look at the schematics on the output on the inverter on the drive, it's pretty easy to see what's happening. It's simple, but it's happening really quick. And that somebody figured out how to create this signal that would allow you to control the speed of the motor. Of course, speed of the motor is determined by, or in part, the voltage that you send it, or the frequency of the voltage that you send it. And historically, it's just hard to control frequency in a power system. Everything was 60 hertz back when I was a kid. Well, look now at the top here. My scope meter tells me it's 267 volts. Let me come back to the drive. If you can see that, can you read? The drive says it's 230 volts. Now we're looking at voltage on the output of the drive. This isn't as big a difference as we saw when we looked at amperage on the input of the drive, but it's significant, right? It's 30 volts out of 230. Well, if you know much about Fluke, you know the Fluke 87. This is, I'll say with pride, probably the most popular meter for a high-end kind of industrial electrician, right? That's used by folks who do instrumentation, the electrical guys. So if you got a dispute, I've got meters reading two different things. You pull out an 87 and ask it. And if you look, the 87's telling me it's 260, almost 263 also. So the Fluke 87 tends to agree with the scope meter. But when I ask customers, what do you want to believe? Everybody wants the drive to be right. Okay? Well, if you have a Fluke 87, you may not have noticed the little yellow second function here beside the volts, next to the volts AC selection. Tell me if I push the yellow button, it'll add a low pass filter in line with the measurement. and now the meter matches the drive. A low pass filter is bandwidth limiting. It's cutoff filters a little more than 400 hertz. I forgot exactly where it is on this one. But you remember earlier I said that the bandwidth on your meter will largely determine your success if you want to get a meter reading that matches what the drive up here tells you. Let's see. I believe I'm going to stop this just so we don't have to listen to it. So here's the numbers, right? The drive's telling me it's 230. The scope meter and the Fluke 87 initially had something up in the 260s, right? When I push the little button on the 87.5, it begins to match the drum. Had I used the 376 FC, it would have matched the drive also. The 376 FC and the 378 FC, they both have a low pass filter that's always engaged just so you can get readings that match a VFD. We have, I don't know, half a dozen tools. Actually, the scope meter, I could put it in what's called the VPWM for pulse width modulation mode and get a number that matches the drive. Well, you saw this display without the amperage. Here, these readings across, or these, three images on the top. Voltage is the waveform above, and then the blue one is the amperage. And what you see is that the amp draw of the motor follows the envelope of that waveform, right? And if you zoom in on that waveform, you get the pulses. You see, I've zoomed in from here. You get the last few negative pulses before the positive. You see the width of the pulses. The pulses get wider as you go to the middle, then they get narrow again. It's actually, the motor integrates the voltage or the current to the motor, which tells me what the motor's doing. It's integrating the voltage. So it's controlling the width that allows you to control the frequency that the motor's running at. And to me, that's just pretty smart. Who figured that out? I'm impressed. But anyway, we don't really have a whole lot of time to spend on that. I want to point out a couple of things, though, on the output here. The carrier frequency is the frequency of occurrence of these pulses. That's typically around 4 kilohertz. So I've got some much higher frequency stuff going on there than the 60 hertz that this thing's running at. That's what the low pass filter on the meter gets rid of. But it's also just high frequency stuff going into a network that has a lot of capacitive and inductive components out there. You know, the motor is a big inductor. The cabling is capacitance. So I've got the carrier frequency, but also the switching speed of these transistors. These transistors are just switches. I don't have it written on the screen, but dV/dt, the change in voltage over time, is how fast the voltage goes. If I look at one pulse from 0 to whatever it is there, you know, would be the rise time in the pulse. As the electronics has gotten better and faster, those frequencies are going up, and that's what causes this term reflections you might have heard. If I look here, I've selected drive output, voltage modulation, phase to phase. So here's essentially the same thing we were looking at earlier on my little drive, right? You can use the zoom button to zoom in and see this pulse right here. You see the rise time is pretty quick. It has no ringing and no overshoot on it. Now, on this same application, and I wanted to be sure and point this out, on this same system, right? Here we're measuring at the drive is where the test leads are. Here we're measuring at the motor, making the same measurement, and you see some reflections. You see the little voltage spikes there. If you zoom in, you see the spikes. I don't think they're significant enough to cause damage, but the voltage spikes can be, depending on who you ask, 2 or 3 times the level of the DC bus. So if your DC bus is sitting at 700 volts, you can get a 2000 volt transient out of that thing. And that is because of the impedances out in the system, the cabling, the motor itself. and the high speed stuff that you're throwing at it coming out of that inverter. And so when we go to the motor in this system, you see the transients and you see a little bit of ringing there. That's that little reactive impedances in the cable coming into play. I don't have time to do these, to show you these, but my little demo kit, I've got a lot of cable, a really tiny motor, and I wanted to show customers a nice looking PWM signal. But when I first wired it up, I was getting all kind of reflections. I traded a voltmeter for a terminator to a Rockwell guy, and with the terminator on, it looks real good. Without the terminator, it's horrendous. Anyway, I think probably terminators aren't used as much as line reactor and active components, but again, that's Lorenzo's area, not mine. I want to show you one other thing, another measurement we can make with the MDA that's built in. I hear this fairly frequently. A problem with bearings that drives sometimes get blamed for is fluting. If you look here, this is the outer race of a driver. You can see it there. This, I want to call it washboard effect, but only old people like me know what a washboard is. It's kind of like the rumble strip down the side of the freeway that your tires hit when you're trying to send text while you're driving, right? This is arcing internal to the, or voltage arcing from the shaft, which is connected, you see where my mouse is, to the inner race of the bearing, arcing across to the chassis, which is grounded on the motor. That is, it arcs from the inner to the outer race of the bearing, and that's what causes this damage. So you can easily measure the voltage on the shaft. And this is a special little probe. That's a carbon filament probe. And just essentially hook it up to a scope, or you can do it with a meter. But here's an example where I made measurements at one of our customers. And too long a story to go into details, but they had a whole table. We were in kind of a lab area. Table was full of bearings with fluting problems. And sure enough, we hooked it up and measured. You look at the setting, that's 2 volts per division, 2, 4, 6, 8, 10. I don't remember seeing more than 10 or 12 volts. So it's very low voltage, but it's cooking those bearings, which amazed me. Now, in this case, it turned out, and again, it's too long a story to go into, had nothing to do with the drive. The drive experts were there, and everybody was talking about DVDT and the switching speeds on the output of the drive. And it turned out this was a textile plant. They were spinning nylon fiber, and it was static electricity coming from the load. It had nothing to do with the drive or the electrical system applied here. Anyway, well, I've got to stop. I see it's 10:59. Some of the mechanical stuff we're not talking about. You probably know about the value of temperature and vibration measurements if you're doing predictive maintenance. That is, trying to use data to determine when something's going to fail. Another little word from our sponsors, this meter, the 805FC, it's just a little vibration meter that also has a bearing test built into it. Well, I'm going to stop there, Robert. I'm looking at, my clock just said 11.
Yeah.
So I'm done.
Oh, okay, perfect. You know, I was chatting with Rick earlier, and I was concerned, how could Rick fill up, 45 minutes on information on measuring drives? So kudos to you, Rick. Very well done. Great presentation. I want to thank everybody for their time attending this Talk Tech with Turtle presentation. Next week will be the next presentation, rather, will be on September 16th, 11 a.m. to 10 a.m. 10 a.m. to 11 a.m. featuring HMS E1 products. Remember, you can visit Talk Tech with Turtle by going to YouTube and searching Talk Tech with Turtle to view past presentations. So thanks, everyone, for your time. Enjoy your weekend. Happy Labor Day, and I hope to see you at the next Talk Tech with Turtle.
And just before we
Thanks,
go, if
everybody.
anybody has any questions, we didn't have anything in the chat, but if anybody has any questions for Rick or Peter, now would be a great time. All right.
Yes,
Right.
there is a question.
You still have, you
Yeah,
still have one
hello.
guy stuck in the lobby, huh?
Hello?
You still have one person stuck in the lobby, I see.
Yeah, we spoke to him. He's
Yeah,
got a
we've been speaking
firewall
to him
that's
on the
blocking
phone.
it.
He was having trouble with his firewall. We were trying to get him to enter in, but I did have a conversation with him, and that's what I can say about
I
that
think
one.
Ron has a question. Go
Yeah,
ahead,
I
Ron.
did. You brought up earlier about the scopes and the connection and whether or not they're isolated. You mentioned that the reference connections are all connected together. Did I understand that correct?
Yes, now
Okay.
depending on the scope, right?
Okay, that's what I was going to ask you. If something was listed as isolated, as having isolated inputs, does that mean that the references are still connected?
If I think that you could say we've got isolated inputs, meaning it's not connected to the ground on the plug, right?
Yes.
If I think by code, can you still see my screen?
Yes, I can.
Okay, if these connectors say are metal, typical B and C, then
Yes.
anything metal, since it's got to be connected to ground.
Okay.
But if you so these are plastic, but these things run on batteries too, the scope meters. On
Okay.
the Fluke scope meter, the 120 series scope meters
Yes.
and the older, the 90 series, they are isolated from ground, but the reference inputs are common.
Oh, okay.
So you could measure voltage phase to phase on one input, no problem. And on the other input, put a clamp if you want to measure volts and amps at the same time. But I wouldn't advise, making two voltage measurements if one of these connectors is connected phase to phase. Is that
Yes, I understand.
okay?
Okay. All right.
Great. Well, thanks, Ron.
You're welcome. Thank you. Great class. Great course. Learned a lot.
Thanks, man.
Great.
Thanks for attending,
All
Ron.
right. Once again, everybody, thanks for your time and enjoy your lunch.
See you later.
See ya.
Have